Okay, this chapter is about light and image formation. And the first thing we want to talk about is called the law of reflection. Alright, so the law of reflection. And you may be wondering, what exactly is the law of reflection? Well, the best way to describe the law of reflection is to think about mirrors. Alright, so let's say I have a mirror here, and this represents that the mirror is solid on this side, right? So this is the non-reflective surface. And this is the reflective. Right? So what does this mean? Okay, well, imagine that I have a horizontal line that's perpendicular with my mirror. Right? Now, up here, imagine there's a light bulb. And it's shining a beam. Let me erase that. Let me do a little bit better light bulb here. Alright, so here's our light bulb, and imagine it's shining light out in every direction. Alright, now let's look at this beam, specific beam right here. This beam's going to come in, and it's going to hit the mirror, and we want to know what angle is it going to bounce off with, right? What angle will it bounce off with? Well, you might be able to remember from common experience, if you've ever shown a light bulb or a laser beam at a mirror or something, the light beam reflects off. We know it's going to reflect off in this direction. And if we want to know exactly what angle will that be, well, it turns out that if I know the angle that my flashlight makes, we'll call this angle of incidence, right? If I know the angle of incidence, and then the angle of reflection will actually be symmetric about this horizontal line here, right? We call that the normal. And the law of reflection essentially says if you have a normal that's perpendicular to a mirror or a reflective surface of any kind, and you shine a beam of light onto that surface, then the angle that the beam hits the mirror with will be equal to the angle that the beam is reflected with. And that's all that the law of reflection says, right? But there's another R word, and that would be the law of refraction. Right? The law of refraction. And this has to do with the principle, a lot of us have seen this before. If I have a pencil and it's just sitting out on my desk or in air or something, then it just looks like a normal pencil. But imagine that I have a jar of water here, and I put my pencil in the water, then it kind of looks like this thing. The two images don't line up. And this can be a little puzzling at first, and so we want to see exactly what's going on. So let's first figure out exactly what's going on. So this effect happens when the pencil moves from some substance like air into a substance with a different density, in this case, water. All right? And so one thing we may be able to conclude is that if I'm looking at the same object in two different mediums, two different mediums with different densities, then maybe this effect would be apparent in just about every case. And it turns out that that's more or less true, right? So what's going on here is that we have two mediums that have what are called that have different what are called indexes of refraction. Indexes of refraction. And this is simply the index of refraction. We denote it by lowercase n, and it is a measure of how fast light can travel through that medium. Now it turns out that air is a very, very low index of refraction. And so for all intents and purposes, the speed of light is unchanged in air. And so we say that n of air is equal to 1. Okay? The n of air is equal to 1. And what that means is that the velocity in air is equal to the speed of light c divided by the index of refraction. Okay, so this is a particular statement of the more general equation. For any velocity in index of refraction I, the velocity can be found by taking the speed of light and dividing it by that substance's index of refraction. Okay? And for air, we see that if n air equals 1, then the velocity in air is equal to c divided by 1, and then the velocity of light in air is just equal to c, or the speed of light. All right? But what about things like water or glass? Things that have a little bit more density than air. What about those? Okay, so going back to the water and the air with the pencil, now just imagine I have a sheet of water, right? And we'll call this N1, and we'll let this be air. We'll call this N2, and we'll let this be water. Okay, so imagine that I have waves of light. Here are the wave fronts. Let me make them a little bit bigger. So the wave fronts for this particular beam of light might be this large, and then when they hit the water, here, the beams get scrunched up. So if these lines represent the wave fronts, then the distance between each wavefront represents the wavelength. So this would be the wavelength in air. And then as they move into the denser medium, the wavelength gets smaller. Right? The wavelength gets smaller. Now, here is something very, very important to note. When light moves from a less dense to a more dense medium, the wavelength and the speed change. But the frequency stays the same. Okay, so if we go back to our wave equation, remember that the velocity of any wave can be described by its wavelength times its frequency. And for light, the speed of light is just c, so the speed of light equals the wavelength of an electromagnetic wave, or a wavefront, times the frequency of those waves. And when we move, when we shine a light on from air into something like water or glass, we're changing the speed and the wavelength, but f stays the same. All right, so that's very, very, very important to note. But if we go back, right? So notice that the wave fronts start to scrunch. I think I spelled that right. So they start to scrunch or bunch up, right? And this is the type of effect that is happening here, okay? So the wave fronts are changing direction. Now, what about when we have the pencil, all right? What about when we have the pencil in the water? Remember that inside the water, the pencil was at an angle. So it did something like this. So let's take a larger tank of water here, and let's give it some water, and let's let some wave fronts be coming in at an angle like this. Well, what happens when these wave fronts hit the water? Well, because the frequency changes, right? Because the frequency changes, or I'm sorry, because the wavelength changes, that will change the direction of motion. So they won't be moving in this angle. They will be moving at an angle that's bent inward in this case. And so when the wave fronts hit the water, these waves will be bent at an angle that is like this. So now the wave fronts will be not lined up, right? So these wave fronts in this region are traveling in a slightly different direction due to the bending at the surface than the wave fronts in this direction. And that's why we see the quote-unquote break in the pencil. Right? And if I look at my normals, okay, so here I have a normal, and because the surface of the water is approximately perpendicular to the normal, then it will be approximately perpendicular in the air as well. But let's say that I have a beam of light that comes in right here. And what happens now is, again, if this is air and this is water, then this is going to get bent inward like this. And I'm going to have a different angle with respect to my normal. So with the law of reflection, when you're in the same index of refraction, like air, then the angles that your beam of light will hit your mirror with will be the same angle that it reflects off with. But in the case of refraction, when you're moving from one medium to another, the angle will indeed change. Okay, so that's the bottom line there. But can we summarize or determine if there's a relationship between N1 and theta 1 and N2 and theta 2? And it turns out, yes, there is. Okay, so this is the law of refraction. Right? The law of refraction says that whatever my initial index of refraction is, times the angle that my light beam makes with respect to the normal, that will be equal to the second index of refraction times the angle that the beam then makes with the normal. Okay, so the product of these two must be constant. And so what we can see is if we're going from a less dense to a more dense medium, right? If N2 is larger than N1, then for this product to be constant, theta 1 must be larger than theta 2, right? Okay, so let's do a quick example. let's suppose that I have a beam of light coming in, and I'm in air, and my initial angle that it makes with the normal here is 30 degrees. And the beam then enters the water, which has an index of refraction of approximately 1.33. Okay? What angle will it make with the normal? Right? What angle will this make with the normal? Well, it turns out, and so if we take n1 theta 1 equals n2 theta 2, then we can solve for theta 2 by dividing both sides by n1, or n2 rather. And remember that n1 is 1, and theta is 30 degrees, and n2 is 1.33, so theta 2 will be approximately 30 divided by 1.33, which is about 22.5 degrees. Now, one caveat, all right? One caveat is that this formula is best when the thetas are small. It works best, all right? As theta gets bigger, then we have to introduce some correction into the formula. But for when theta is fairly small, and it really works really well when theta is smaller than about 20 degrees or so. All right, when theta 1 is less than 20 degrees or so. But if we go back, all right, so we can see that this will be about 22.5 degrees. So if I get rid of some of this here, then we can see that the light beam will change its trajectory by about this much, right? So it's not a huge bend, but it's a little bit. All right, so that's the law of refraction. But now, I want to ask you this. Have you ever wondered why a fish doesn't appear to be where it is? Okay, have you ever wondered why a fish doesn't appear to be where it is? And this is similar to the straw in the water. This has to do with the law of refraction. If you look at a fish tank from the side and then from the top, the fish doesn't appear to be in exactly the same place. And let's discover why. So, let's say that we have some water. Let me lower that just a little bit. I'll want some space up here. So imagine we have some water, all right? And here we have a fish, okay? And the light coming from the fish, so this is really sunlight traveling through the water and then reflecting upward, but let's imagine a ray of light coming from the fish, and a ray coming right from the fish that will move straight up will not be refracted at the surface, and it will continue to move straight up. But what about a beam that moves off in this direction right here? Okay, what will happen? So now, remember, this is water, and if when we moved from air to water, that the beam got bent toward the normal, or the angle got smaller, then in this case, if this is my angle, then in this case my angle must get bigger. We'll call that angle W for water. then my angle must get bigger. So my beam of light might do something like this as it comes out. So if I have an eye here, with some eyelashes, okay, so if I have an eye right there, then they're going to see the fish. If I trace this back, they're going to see the fish right here, when in fact the fish is a little bit lower, right? So we call the distance from the fish to the surface, we call that the object distance. And where the fish's image is, the distance from that to the surface, we call that the image distance. All right? And it turns out that n1 times the image distance is equal to n2 times the object distance. So if I want to calculate where the fish appears to be underneath the water, if I know how deep it actually is, then I can find it. Or vice versa, if I know approximately how deep the fish appears to be, then I can calculate how deep it actually is. So let's do that real quick. So let's say that my fish appears to be half a meter below the surface. Like if I'm just looking at my fish, I would guess, oh, it's about half a meter below the surface. How deep is it really? Well, we just go back to this equation, Ni equals N2O, and I equals 0.5, and 1 is 1, and so N2 is 1.33, I apologize, hang on just a second. So what's actually happening is that inside the water, wherever your light beams are generated, that is N1. So the water is N1 and the air is N2 in this case. So N1 is still water. So in this case, this is 1.33, and N2 is the air in this case, right? So wherever your light is originating from, that is N1, and then where it gets refracted to would be N2. So in this case, the air is N2. So 1.33 is the water, N2 is 1, right? And so let's find where our image and our, well, we know what our image is. Let's find where our object is. So we have Ni, or N1 if you want, I equals N2O, where N1 is 1.33, I is 0.5, N2 is 1, and O is what we're looking for. So if I solve this equation algebraically first, right, divide both sides by N2, then I get O, not theta, but O is going to be equal to my image times N1 divided by N2, which in this case is going to be 0.5 times 1.33, because 1.33 divided by 1 is 1.33. So 0.5 times 1.33, and remember this is in meters, and so 0.5 times 1.33 is 0.65 approximately. All right, approximately 0.65 meters. All right, so that is how to determine the actual depth of the fish, or vice versa. If you know the depth, then you can calculate the perceived depth if you know what the indices of refractions are. All right. Okay, so that's it for this lesson. In the next lesson, we will look at image formation with lenses and with mirrors, and that will finish out the chapter. All right, we'll see you then.